Okay, welcome back to the Fall 2021 Hottest Seminar Series. This week's speaker is Mathieu Sozeau from INRIA Nantes, and he'll be speaking about the MetaCoq project. So take it away.
Thank you. So yes, I will today talk a bit about the MetaCoq project, which is not directly hot related, but related to how we can trust proof assistants. And it's been a long project with many participants over the years. So here are all these people, if you want to see, pictures. This is the MetaCoq team. And we've worked mostly on formalizing the theory of the Coq proof assistant and try to get something close to the implementation of Coq in OCaml, written itself in Coq and verified with respect to a specification. And there are many issues with that. The motivation is kind of obvious. We are verifying a lot of artifacts in proof assistant, compilers, theorems, that require some computation, like the four-color theorem. We can formalize homotopy type theory in a proof assistant, and we can also produce artifacts thanks to a compilation of these formalizations, so extraction or direct compilation. So we produce verified C compilers from the ComCert project. DeepSpec as a verified web server that's been formalized in Coq. From the four-color theorem, you could also extract a verified coloring program, etc. But so all these things are nice and formalized, but what about Coq itself? And what do you really trust when you are verifying a proof in Coq and you have a QED, so you're very happy, but what did you really verify here? So we will make a distinction between two versions of Coq, the ideal Coq that the theory we would like to implement, and what's actually implemented by the reference implementation. There is a single implementation of Coq, but actually Lean has a very close theory as well to Coq. And how do these implementations relate to the specification? So we are going to focus not on all of the proof assistant, but only on its trusted kernel, the trusted core of the system, which is basically a dependent type checker, which in Coq is around 20,000 lines of code that's been developed over 30 plus years with many different implementers. And it does type checking for a theory with inductive families with a specific guard checking algorithm to verify recursive and co-recursive definitions, their termination or productivity. It has universe cumulativity and polymorphism, an ML-style module system that was developed over many years that had many iterations. And it contains 3 different implementations of fast conversion procedures. So apart from the naive conversion procedure that corresponds more or less to what you have on paper, or we'll see that it's not exactly true. We have also specific conversion machines that are used when we are doing intensive computations, for example, on large numbers. When we write reflexive tactics where we need a really fast reduction of Coq terms. And of course, this is implemented in OCaml. So when you do anything with Coq, you are actually relying on OCaml's compiler and runtime being bug-free. And that's something we would like to remove, or at least give a reference implementation of Coq which does not have this dependency. So the reality between the ideal Coq and implemented Coq is a bit sad in the sense that ideal Coq, so the theory that we imagine Coq is implementing, is actually unspecified or very loosely specified. And we find that the implemented kernel is buggy. So more specifically, the specification of Coq is not written out entirely in a single place. It's spread over the reference manual in a kind of semi-formal and partial way. So not all the features have been put together and specified formally with inference rules, for example. And that's mainly due to the complexity and the fact that it's a collaborative project that's been extended by many different people. Sometimes a subsystem was extended multiple times, refined over time. And we have the situation where one feature in the kernel corresponds to n papers or PhDs for many different features. And of course, this leads to discrepancies with the OCaml implementation, even between the paper presentations that we can find and what is actually implemented in OCaml. We almost never have a direct translation between them. And finally, due to the fact that we have all these extensions coming from different places, the combination of features have not been worked in detail. In particular, for example, when we added cumulative inductive types, we did not think about the fact that in inductive declarations in Coq, you can have let bindings that appear. So you don't have only assumptions in your context, you also have definitions, so let bindings in your context. And does that interact in any way with cumulative inductive type? You don't know until you've hit the bugs that appears. On the side of the implemented Coq, of course, you see that due to these combinations of features, you often get bugs and critical bugs from which sometimes you can prove false that are coming from the combination of features. For example, here you see the VM compute, which is a fast conversion algorithm, had a problem with the universe polymorphism, or sometimes even just substitution functions are not completely implemented because we added these let bindings in the syntax at a later stage, and nothing is really here to help us check that we don't miss any case when we add a new feature. So our goal is to improve trust and reduce the gap between these two things. And first, to provide a full specification, so of the theory, so that we can really trust, and then see if an implementation can be put in front of that. So the talk will be divided into two main parts. One about the calculus that we define, that contains a lot of the features of Coq, not all of them yet. And a second part in which I will focus on the verification of a type checking algorithm, in particular of a conversion algorithm for this theory. And all this is done in the MetaCoq project, which started as just a simple plugin for verifying and denoting Coq terms so that you can have access to the AST of Coq terms in Coq itself and write plugins, translations on this. And of course, this is all implemented in Coq. So I'm going to do a short demo of this. Stop share again. Okay, so here I'm in Coq and I imported the MetaCoq libraries. And the most central definitions that we have in our in this library is a definition of terms that by design should look very close to what the Coq kernel sees as terms. So the syntax is almost the same, except for imperative features like arrays that are part of OCaml that we don't have in Coq. So they are replaced by list. As you can see, it's a quite big AST. We have many nodes. I'm sorry, I need to get some water. So in Coq, we have two kinds of variables that are represented. You have this tRel for De Bruijn variables, so local variables for lambdas and pi's, and you have these name variables that are only appearing inside goals. So you have a locally nameless representation in goals that uses this tvar. There are existential variables, sorts, which are annotated with a universe, which might be prop, set, or type with some universe levels. We have a cast construct that allows to force the type of a term, dependent product and lambdas, and these letins, which are unusual in standard presentations of type theory. You usually don't see letins, but they cause some trouble in the theory. And applications here are application of a term to a list of arguments, and there is an implicit argument in the representation of of Coq terms in a camel, that the list is never empty, and that this term is not itself an application. So you have no nested applications, and you can access the head of an application in constant time. Then you have references to constants, inductives, and constructors, case analysis, projections out of records, and then fixed points. And the last two were added very recently. There are primitive integers and floating point values inside the system. Okay. So MetaCoq provides comments to quote and unquote regular Coq terms into this AST. So here I reify the identity function on natural numbers, and I look at its syntax. So it's going to be a lambda abstraction, reference to an inductive type, and then a double index corresponding to the variable reference here. And similarly, we can do the converse for a well-typed an AST corresponding to a well-typed term. We can unquote its definition to get a definition in Coq. So here, sorry, the AST corresponds to the first constructor of the natural numbers type, which then is interpreted as a 0. We define a small monad to be able to call functions on the Coq side and manipulate these reified terms or add definitions to the global environment of Coq. So this is the MetaCoq monad. It allows to write little programs that do quoting, make definitions, and so on and so forth. So instead of writing these MetaCoq code definitions, I can always write a template monad program that does my manipulations. So I have freedom in to develop plugins or translations using this. So here sorry. Okay, here, so I quoted 3 plus 3, and I asked the system to print this information. So it just prints out the AST corresponding to 3 plus 3, which starts with an application of addition to the representations of 3 and 3. I can also write interactive comments that ask the user for some information. So here I ask for a value of type natural numbers, which will be we will ask the user to provide this value and define a lemma foo44 with its value. Then I can quote the resulting value, evaluate it, and print it. So here I'm providing the natural number that is asked by this plugin. I can define it, and I can look at the definition of. I can look at the output. Sorry. I put 3 plus 2, and then I quoted it and evaluated it, so I get 5 as an answer. All right. I'm not going to focus much more on the monad for the rest of the talk. Then we have definitions of the typing judgment of Pickwick, so the theory of Coq, or the idealist theory of Coq that we want. So this is an inductive characterization of typing, which relies on a global environment extended with a declaration of universes for the local universes in a universe polymorphic definition. And the global environment contains declarations for inductives and constants. Then we have a local context, which contains either assumptions or definitions. And then the usual 4-place relation, sigma, gamma types, the sort S as type sort universe of dot super of S in sigma gamma. So the subject and the type. Okay, and we have typing rules for each of the constructs I presented before that are more or less as you can expect. So I'm just showing you the Latin typing rule, which you might not know because it's a bit unusual. So Latins are basically typed with Latins themselves. Okay, and you just type the body of the Latin in a context extended with a new definition. with a name NA here, body B, and some type. Okay, and you have an obvious reduction rule which just reduces the Latin by substituting the little b here in T. Okay, so we'll see in the talk that we can develop the meta theory of the system and prove standard theorems about the syntactic meta theory of type series, like subject reduction here, which says that if I have some term little t in big T and I reduce it, then I have type reservation. So you will also have this this type. In the second part, we will see that we can also implement a type checker and a conversion checker for this theory, which we will show is sound and complete. So this is conf term is a function that decides if two terms here, T1 and T2, are convertible or not, and it does that computationally by comparing these two terms, reducing them to weakened normal form, comparing the heads of the normal forms, and so on and so forth. And to be able to define this in CoQ, we have to show that this is terminating. And to do that, we will rely on an assumption that every well-typed term is normalizing. And all these functions are dependently typed, and will have assumptions that the terms that we want to reduce are themselves well-typed, and will preserve that information. So we'll be able to show that this conversion function is yes.
But you're not proving that the normalizer terminates, right? Because obviously you cannot do this in CoQ itself, right?
No. We are assuming a normalization on well-typed terms, and using this axiom, we have the definition.
Okay. So that's an axiom which you just assume. Okay.
Yeah, I will come back to it. Yeah.
Are well-typed terms defined inductively using intrinsic syntax?
No, here is just a sigma type of a type and a proof of this derivation. So we start from the raw syntax, like CoQ does in its implementation, and we just undo these terms with a proof on the side that that is well typed. Okay. So we cannot just be checking terms. We need also to check the global environments that are present in CoQ. So inductive declarations and constant declarations. Constants are easy, but inductive declarations are quite complicated. You don't only have typing invariants, you also have positivity, a positivity criterion to check on your inductive definitions. But all of this can be verified and decided inside CoQ. Okay, I'm gonna skip this. Even though, as Thorsten pointed out, we are relying on an axiom of normalization, saying for any well-typed term, I can reduce it, and this will be a well-founded process. It will stop at some point. We can still run on concrete examples the type checker inside CoQ, and we can use that to help when writing plugins to discharge typing obligations of the terms that we are producing. So here I'm making a goal that asks that I provide a proof that for all, so it's a bit unreadable, but this corresponds to for all A implies A. So the type of an identity function. And I can provide a term for this function, so the obvious one, that just does lambda A, lambda X, X. And ask the type checker to produce the proof that this term is well typed. And that can be actually run inside CoQ. Finally, we can extract this type checker that we've written in CoQ to OCaml, and also run this program in OCaml instead of inside CoQ. Yes. Okay, so this MetaCoq self-check function calls OCaml code that is built from the extraction of the type checker that we've written in CoQ. Any questions?
Yeah, so how does it happen that your type checker does not get stuck on this postulate? Because I would think normally if you postulate termination of something, then your function has to block on that postulate, because otherwise you would lose strong normalization, right?
Yeah. So
What's
the
the
trick
trick
is,
to work around it?
the trick is that, so accessibility proofs, you can make kind of fake accessibility proofs that are unfolded for a finite number of times before you get back to the axiom. So you can hide your axiom under a lot of intro, of constructors of accessibility, and that means that you can do as many unfoldings without getting stuck. So if you put a large number here, it's a very large number of accessibility constructors in front of your proof, you can run it at least on these examples.
Right. Okay, I see.
Yeah. Okay. Back here. Okay, so now I will present a little bit more about this the calculus that we are formalizing, which is called the predicative polymorphic cumulative calculus of co-inductive constructions. It's a mouthful, but basically it's an extension of the calculus of inductive constructions with polymorphic universes and inductives where cumulativity of universes goes through inductive types. And what did we formalize with respect to typing? So here I'm showing you the definition of VREV on vectors, which kind of puts together a lot of the features of the calculus in a single definition. So we can, of course, yeah, at the bottom I'm giving you the reification of this definition. So we formalize fixed point and co-fixed points, but we're gonna use an oracle for the guard condition. So our assumption of strong normalization is actually if the is also relying on the fact that we can design a reasonable guard condition on our definitions, and these are the only two oracles and axioms that we are using. But other than that, we have the usual fixed point reduction rule, which checks if the principal argument is reducible to a constructor object for unfolding. And same for co-fixed points must be forced by a pattern matching, by a match to be reducible. We have the full dependent match rule, so dependent case analysis for inductive families. As I said, we have universes, universe polymorphism, so you can abstract on this level variables. And we have this lead binding construct in the system as well, and general inductive families. What we don't currently formalize are the, the eta conversion rule, which was added to Coq about 10 years ago without really a full theoretical justification, and it's actually very hard to justify its presence in the current setting of untyped conversion. I will come back to that at the end. We also don't support template polymorphism, which is a kind of poor man's universe polymorphism that was implemented a long time ago, and that could be better understood as something that can be elaborated to a usual universe polymorphism. And that's the plan for us to tackle this feature. And finally, we don't try to formalize the module system, which is a huge part of the system, but mostly orthogonal to the core features of the language. Finally, we have existentials and name variables in the syntax, but we don't type them yet. It's left for future work. Yes?
Yeah.
Sorry, don't hear. Carlo, should I listen to a meeting or is it a bug?
Yeah. I was trying to figure out who that was, but you should.
Oh, it's a bug.
Yeah, continue.
Okay, I can continue. So as I said, we have inductive predicates to represent the various relations in our specification. So here I'm showing you the definition of reduction, and I'm focusing on the lead bindings, the lead binding rules. That lead bindings are subject to 3 rules of reduction. If you have a definition in your context, you can of course expand it. If you have a lead binding as at the head of your term, you can also expand it. So just substitute the little t, the body of the lead inside the prime here. And there's also, as usual in dependent type theory, congruence rules for all our constructs. So in the case of let, you can reduce directly inside the body of a let by just putting the definitions, so the definition inside the context. So in the hypothesis of this last rule, you might have expansions corresponding to the first rule happening. Okay.
Sorry.
So,
the
yes?
the context is part of the reduction rules, but not the type.
Yes.
So it's
Yes.
untyped reduction, but you know about the context.
You know about the context, but you don't have types.
Okay.
Yeah. Okay, and of course you have all the other usual reduction rules and congruence rules for reduction. Okay, so I presented the term structure. We have a bit more structure to define. To be able to define this calculus. So the global environment, which contains declarations. So they associate a kernel name or a unique identifier to an inductive declaration or a constant declaration. And when we are type checking polymorphic definitions, we also have a universe declarations corresponding to the universes declared just for this definition or inductive type. And these local environments are just lists of either a name and a term. So it's not just a name, it's a name and a relevance annotation that's used for to implement the S-prop conversion rule. But you can basically think of it as just a name. And so we have assumptions, a name with a type, or a name, a body, and a type. So the judgments that I've presented, we have one-step reduction. We can take it with reflective transitive closure to get full reduction, an alpha equality and alpha cumulativity relation. So it's doing alpha equivalence plus the relation of on universes that's determined by the various constraints we have in the global environment. Similarly, for we don't have just conversion, we have cumulativity in general. So we have a kind of subtyping relation for universes. And once we show confluence, which we can show for this calculus, we can show that this relations correspond to just reducing the two terms to terms in the alpha equality or alpha cumulativity relation. Finally, typing and the notion of typing corresponding to global environments and local environments. Okay, so we can show the basic meta theory of this calculus. It's fairly standard, contrary to what is done in CoQ, where there are lifting and substitution operations. We have more general renaming and instantiation operations, which enjoys a nice algebraic laws of sigma calculus. So we still keep both definitions to relate to the CoQ implementation, but we are using renaming and instantiation everywhere. And we can show weakening and substitution from renaming and instantiation theorems. Okay. As I said, universes are either prop, S-prop, or typed, applied to a non-empty sorted list of universe levels. And we have here a difference with what's implemented in CoQ. In CoQ, there are restrictions on which universes can appear in a derivation. Here, all universes are always allowed in a derivation, so there is no distinction of algebraic universes. It is so more uniform than QNCoq and similar to what Agda or Lean have as a universe expressions. And universe constraints are just constraints corresponding to some level plus some constant in Z is less or equal than another level.
So what are algebraic universes, Mathieu?
So algebraic is a case where you have more than one level. So it's a max or a +1. So non-algebraic universe are just the levels.
And so what is the difference? What's the meaning of
Usually don't see the difference. There is no, I mean, there are no specific algebraic universes in Agda or Lean, for example. All universes are the same, but in Coq, there is actually a distinction between a universe that is made of just one level or a universe that's made of either multiple levels or some levels incremented by a number. And that's a pretty thorny issue in the representation of universes in Coq. But here I'm just, so the theory here is more general and encompasses the theory of Coq.
But you see it's similar to Agda, basically. Okay.
Yeah.
I misunderstood this first. Okay, thank you.
Yeah. So the usual specification for universes is that we can assign natural numbers to the levels and get a global set of consistent constraints. And here we have a source in this set of constraints, which is a set, so the lowest universe, which has level 0. And we consider impredicative sorts, so prop and S-prop here separate from the predicative hierarchy. We can show standard structural theorems about the theory, so we can weaken the global environment by a new global declaration and get the same typing. Universe instantiation is fairly easy to verify. But for the implementation of universes, actually the implementation and the specification are based on the same longest simple path algorithm that generates a graph given by the constraints. And oops, sorry, I cannot show it. Okay, so using this longest simple path algorithm, it's easy by looking at the length of the longest simple path between two universes to know what valuation corresponds to the universe. After this, we can try and prove subject reduction. Before that, we need to show validity, which is not direct from the typing rules of Pickwick. It's not formalized in a paranoid way, but rather in an economic way. So you need to show validity afterwards. Then we can show context conversion and subject reduction. So actually, validity requires already transitivity of conversion and cumulativity, which, depending on how you formalize conversion and cumulativity, might require confluence. Context conversion is a bit generalized to context cumulativity due to the contravariant cumulativity. And subject reduction, as usual in this with untyped conversions, it requires injectivity of type constructors, which is a consequence of confluence. Just a little focus on confluence. We had to adapt it a little bit because of these Latins that appear in terms. So the traditional way is to not consider one-step reduction, but parallel one-step parallel reduction, and show the diamond lemma for this relation, and then use a squash lemma that shows that one-step reduction is included in one-step parallel reduction, which is itself included in many-step reduction. And from that, we can deduce confluence for reduction from confluence for parallel reduction. There's a little trick due to Takahashi, which allows to simplify or systematize the proof by showing just one lemma about a row function which takes a term and simultaneously one-step parallel reduce all red x's in it. And then we can show a lemma about this row function, which says that for any term u, from which t can be reduced in one-step parallel reduction, u also parallel reduces to rho of t, because rho of t has the maximal number of redexes reduced in a single step. And using this triangle property, we can use it twice to show the diamond lemma for parallel reduction. For this series with definition in context, we need to actually include context in the subject of a one-step parallel reduction, because you might be reducing definitions in the context at the same time you are reducing things in the term. So you get a little bit complicated parallel reduction rules for this for the rules related to lead binding, and you need to extend rho to a function that reduces context in one-step parallel reduction optimally. And using this this extension, we can show the same triangle lemma and confluence for this extended notion of reduction with lead bindings. We can also show in this system where we have subtyping, we cannot show uniqueness of type, but we can show a similar property, which is principality. So every term has a principal type. So all other typings of this term have types that are greater in the subtyping relation than the type we infer here. So we can show for any well-typed term T that there is a principal type P for this term. And using these properties, we can actually justify some of the tactics of Coq that are used fairly often, like the change tactics, which allows us to change the subterm for another in a goal, is really justified by the fact that if we have convertible terms or convertible terms, then we can always replace a subterm with a convertible one of the same type. So we need to restrict a little bit the range of this lemma, in the sense that we cannot do that for all convertible terms, because due to subtyping, you might change the minimal type, the principal type of a term by conversion. Okay. We define also less precise conversion relation on terms and types that does a usual conversion, except that it identifies all predicative universes. And this is a lemma that we actually found out was necessary to prove correctness of the erasure procedure on Coq terms that's used by extraction. So we'll not really focus on that today. But it also tells us that if we have two well-typed terms that are syntactically equal up to cumulativity, then they always live in the same hierarchy. We cannot confuse things in prop, S prop, or type, which is a useful property to have in mind. Okay, so we reduce the Tradestate theory to this basically this specifications of typing, reduction, and cumulativity, which are not too long, and they're verified in the sense that we develop meta theory for them and we can test them. But we still have some assumptions. So as I said, we have oracles for the guard conditions. We did not implement the guard checkers yet. Actually, there is an implementation, but we did not add it to the theory yet. And in particular, because we did not yet prove that these guard checkers are preserved by renaming, instantiation, equality, and reduction, which are necessary for our theorems to hold. And of course, we have a strong normalization. Oops, sorry, you don't see it. Okay. We have a strong normalization assumption, which says that for any term that is well-typed, we can, the reduction relation starting from T is accessible, so it will end at some point. We cannot hope to prove it directly inside Coq, but we can show that just from this normalization assumption, we can easily prove consistency and canonicity for the theory. And it's not used in any of the results I presented before, which hold also if the theory was non-terminating. It's going to be used exclusively for the termination proof of the conversion test I'm going to show next. Also note that it could be inherited by preservation of normalization from a stronger system with a model. So that's actually the plan here to derive this axiom because our theory actually translates into a theory which is normalizing. So verification of type checking. So the goal here is to verify a conversion checker, which takes as input two terms, two well-typed terms, and outputs proof that they are convertible or that they are not. So this is the type of the conversion function. So it takes two typings of U and V. And the algorithm is fairly standard. We can reduce both terms and compare their heads. If there are two lambdas, for example, we recurse by comparing their domains and comparing their bodies. If we have pi types, we do a similar thing, and so on and so forth. So we always we only have to care about weekend normal forms, and we get weekend normal forms by reducing the terms. We need to show completeness of this this conversion checker. And for that, we actually rely on inversion lemmatas that are proven already in our meta theory and the confluence proof for conversion, which ensures that we have these properties. That if the domains of two pi's are different, then of course the pi types will be different. Okay, so the real work happens in the wicked reduction, which takes a term and outputs a term, which should be a reduced term of U. So V should be a term obtained from U by reduction. Okay. So the definition of wicked reduction has to implement all the reduction rules of Coq. So we have, for example, expansion of definitions, and then beta reduction. Okay. So how do we show termination of this function? As you've seen, we need to be able to unfold a subterm and then look again at the bigger term to apply beta reduction. So we actually need to consider not just term, but terms under a context, at least an applicative context. And in that case, we need to find a termination measure to ensure that this is decreasing, starting from the assumption that the big term is well typed, so any reduct of the large term, the large initial term is okay. Okay, so we can apply this. We need to be able to apply the reduction rules under context. So we need at least to consider the subterm relation to be able to do reduction of subterms. And it looks like we could just be using the lexicographic order of subterms and a reduced term, which is well founded thanks to this normalization assumption. Okay. So for projections, for example, it will work. We can reduce P and get to a subterm. But we hit a little problem with fixed points. So when we want to reduce a fixed point, we first, well, actually we just see an application. So we reduce the left-hand side of the application to get to a fixed point. And then the fixed point rule is that we need to check if the principal argument reduces to a constructor. So we will reduce n. And finally, we need to consider the bigger term built from the two reduced subterms. And for that, the lexicographic order is not going to be enough because these two terms are actually equal. No, one is not a subterm of the other, nor a redux. So we need to refine our subterm notion to actually do an order on positions in the terms. So here we will we define a new algebraic structure corresponding to positions in a term. And here you see the three possible positions in an application, either the whole applications or the left or the right, and we can impose an order on positions that will ensure that our wicked reduction function is terminating. But we are actually working on this stacks now. So the actual measure is not just a lexicographic order. It's going to be a dependent lexicographic order because positions only make sense in a particular term. So positions are dependent on the term we are reducing. Okay, so this gives rise to a dependent lexicographic order of reduction and this order on position. And once we have that, we can define this wicked reduction function. Once we have wicked reduction, we can define conversion. It's easy to do a cumulativity check instead of conversion by using the longest simple path algorithm I showed before. And type checking is type inference and type checking are fairly easy in the system. These are just structurally recursive functions on the term. Okay. So when we want to check that T has type A, we do type inference, infer some type B, and we can check cumulativity because we verify the conversion test to have a proof that T is indeed as type A. And we can extract this type checker I've shown you in the demo, this extracted type checker running. Okay, a little success story about this whole deal. Is that we found issues in the implementation and in the specification of the system, and the most interesting one is probably this problem with the match representation inside Coq. So for a long time we knew that we had a little issue in match, in the sense that when you see a match written like as a subject of the typing rule here, you bind P as E, so you give a name to the equality proof here. We're emulating an equality proof. You're giving a name to it to express the return type of this elimination. And you can give names also to the indices of the inductive value. And that's just a kind of compact syntax for applying the usual eliminator on equality. Okay, but here what you don't see is that in the syntactic representation of match, we actually have types corresponding to E and Y, which kind of appear in the typing rule. And there was a confusion inside the implementation about which type should we rely on when we are type checking a match rule. Do we look at the type that is given that we can infer from the scrutiny here, P, so use J and A prime as the universe instance and parameter on which we are doing the elimination? Or do we look at the types that appear, that don't appear in the syntax, but they appear in the abstract syntax tree that we get in Coq? So here, A and I are the things that appear in the AST in Coq, but don't appear in the syntax. So we found out there was confusion in the code and the specification. And we found out by just trying to do the proof of completeness of bidirectional typing for the calculus. And we found out that indeed we had a problem of completeness, that we were using the wrong universe instance, not the most general universe instance and not the most general parameter when type checking the match. And this led us to find that in Coq itself, we had a subject reduction issue by just crafting the right test case. And we also thought, oh, maybe we don't need to change so much the theory, but we can use a structural lemma like a strengthening to justify our a fixed typing rule. But actually, we also found out that you cannot prove strengthening on this formalization of type theory easily, because you have this free-floating conversion rule which allows to pass through types that use variables that you don't see in this conclusion. So that was pretty bad. But we actually, so we went with the change of case representation inside the representation of cases inside the implementation of Coq, but also in MetaCoq. So we did both at the same time. As in the new representation, basically, you can see here in EQ at I, A, T, X. This syntax represents exactly what's in the kernel. At each time you are doing an elimination, you know at which parameters of the inductive type you are eliminating. So you have information about A and T, and you know the universe instance at which the elimination was created. So here, I. And this makes the typing rule nicer to look at. The syntax is now closer to the higher level user syntax. And so it's all good for us. So this was kind of brought up by work on giving a bidirectional version of the typing rules, which are really a good thing for us. Because I brought this issue up, but also these bidirectional rules are easier to reason about, and they provide us a new structural rules. Like strengthening is just direct to show on the bidirectional derivations, and principality also directly follows from correctness and completeness of bidirectional typing with respect to the undirected typing. So we don't need a separate proof of principality. It's kind of part of the equivalence. So in the bidirectional derivations, you have we have one version where every term can infer a type. So it's a bit different from other variants of bidirectional type checking, which either type check only normal forms or use a cast operator to mediate between the two phases of inference and checking. So what they give us is compressed and localized conversion rules, and to show the equivalence with the undirected typing, of course, we need to have transitivity of the conversion to be able to compress multiple conversion rules into one, and completeness requires injectivity of type constructors. So it's harder to have this in a typed meta theory unless you've already proven strong normalization for your theory and injectivity of type constructors. But here it follows easily in the untyped case. Okay. So I want to say a few words about how can we link this untyped specification to a typed equality. So here's a version of type theory we have as this typing judgment and a conversion judgment that's just defined by reduction. And the typed equality judgment that you probably know, that's part of the hot book definition of type theory, for example, is generated from the reduction rules, congruence rules, and also closed under reflexivity, symmetry, and sensitivity. So both are equivalence relations, but for different reasons, because the one defined by reduction is transitive only once you've shown that it's that reduction is confluent. And it's easily shown to be reflexive and symmetric. So of course, if you take typed equality, you can easily construct a non-typed equality from it. The other direction needs a lot more work. For example, if you had subject reduction, you could easily show that untyped equality implies typed equality. But it turns out that if you look at the state of the art for showing subject reduction for a theory with type conversion, it's kind of hard as well. So here I'm looking at the proof of decidability of conversion for type theory in type theory by Abel. And actually, the subject reduction theorem comes very late in the development, due again to the problem of injectivity of type constructors or substitutivity in a type setting. So if you want to prove subject reduction, why is it not simple to prove subject reduction when the equality is typed? You can look at just a beta reduction case for subject reduction, and to show that you are preserving types by reduction, you need to invert a derivation for the lambda abstraction, which you are substituting in. And this inversion of the derivation just tells you that you have a pi type, a pi AB, that will be equal, convertible to pi A prime B prime at some sort S. And to actually show type preservation, you need to deconstruct this equality using injectivity of type constructors, so that A is equal to A prime and B is equal to B prime, and then you can show that the substitution in B and the substitution in B prime are equal. And this is you cannot do that directly in the system unless you use a logical relations argument.
Sorry.
Yes.
Are you now to prove something about untyped reduction, right? Or
no, I'm talking about type reduction.
But type reduction should have subreduction by definition, no? I mean,
what?
It's typed reduction, so it's relation on type terms. So why would you have to prove subreduction?
To show the equivalence with the untyped.
Yeah, that's what I mean.
Yeah.
But who cares about the untyped reduction? It's just wrong. So just throw it
That's
away.
the one that's implemented by Coq. That's the one we want to justify here. So I agree, it might not be useful to you, but yeah.
No, but maybe you should replace it by the correct definition, no?
Yeah, I'm kind of going to that.
Okay.
Yeah. You could think that if you have bidirectional typing rules, you could step away from this problem, because if you have bidirectional typing rules for this beta reduction rule, then you don't need this kind of inversions and injectivity of constructors to deduce that A and E prime are the same and B and B prime are the same. However, you need to show that these bidirectional typing rules are closed under substitution, and that also requires normalization and a logical relation argument. Okay, so our plan is to go this way. So we've shown using a confluence that this undirected typing and untyped conversion is equivalent to the bidirectional typing and untyped conversion. And we can show that this untyped conversion corresponds to the typed algorithmic conversion of Abel, but this proof will require normalization of the bottom theory here. And Abel has shown already that the undirected typing type conversion is equivalent to this algorithmic version. And this is really the theory that corresponds to, I mean, that we think of as a specification of MLTT, for which we have models in CWF, etc. So our goal here is not to do much more work, Thorsten, is just to show that Coq is not doing like crazy things with this untyped conversion. It still has a meaning in the sense that it implements a type conversion algorithm, just not relying on types. But of course, if we want to extend the untyped conversion with extensionality rules like eta conversion for pi types or the unit type, we will need to use the type algorithm, or at least introduce some reliance on type in the system. So the conjecture is that this methodology lives through all of CIC, but there are no reason if it works for type theory with just pi types. A bigger open problem is what happens to the model of Abel and the logical relation definition if we want to handle impredicativity. That's very unclear. Okay, am I doing on time?
You're about at the hour, but I think you can go ahead. Well, depends how much more you have, but you can keep going.
Okay. So I will skip verifying erasure and just tell you that we have this result. So erasure is a procedure in Coq that corresponds to extraction that removes type annotations everywhere and all the content in prop or sprop. And we can show a theorem that if we have a well-typed closed term of type natural number and we erase it, then we also we get the same values for a weak call-by value evaluation of this term. So this is useful to get verified extracted programs out of our formalizations. In particular, the verified type checker can be extracted with this verified extraction. So it's extract to untyped lambda calculus, but there are a few compilers like the CertiCoq compilers that start from this untyped lambda calculus and go down to assembly code in a verified way. So we can really run this this kernel in a verified way. And I think that's okay. It's just a few perspectives on this. So we are actively working on trying to make this picture I've shown work out, so that we can relate the theory we have that is implemented by Coq to actual models of type theory. And ongoing and future work, so we are working a lot on verifying translations from variants of Pickwick to other variants of Pickwick and syntactic models. So that's the work of Pierre-Marie Pedro in particular. There is already a formalization of rewrite rules in this theory that was done by Theo Winterhalter, where he showed that it preserves confluence. But we've not integrated this development yet. Also, maybe I did not say it at the beginning that we don't handle the S-prop sort and the irrelevance checking that is associated to it yet in the meta theory. And it will be interesting to see if we can actually stay with a non-typed conversion while handling this case or not. It's not very clear. And same thing for eta conversion and contravariant subtyping. We've been banging our heads trying to fit eta conversion in this formalization without introducing types everywhere, and it does not look like it's gonna work. And finally, we would like also to formalize an extension of this universe polymorphism to sort polymorphism to deal more uniformly with the different hierarchies we can have in Coq or want to extend Coq with, like a sort for exceptions or sort for setoid types. And that's it. Thank you.
Okay, thank you. So let's keep our mics muted and visually applaud the speaker. And then, yeah, if you have a question, just go ahead, unmute yourself and ask. All right, so I guess I'll start. So, I mean,
Oh, you start. Okay.
Well, maybe I'm asking Torsten's question, but so, I mean, you have eta and you have S-prop, right? And so how are those actually implemented?
Okay, so
I mean, like in the current Coq.
yeah, in the current Coq, yeah. I don't have a picture for eta. So S-prop is implemented using this relevance annotations on binders that I mentioned at some point. For eta conversion, Coq implements a kind of lazy eta conversion. When during a conversion check, you see a lambda on the left and any term on the right, you can expand the right-hand side. So apply the right-hand side to a fresh variable. So we kind of assume that both terms have a pi type, because if the one on the left is a lambda, then the other one should have also a pi type. But it's very unclear in the untyped conversion if this invariant is really holding. You just know that the two terms are well typed when you start with them, but you don't know that they have the same type. Not necessarily, at least. So it's hard to justify. So you do this on the left or on the right. If you have a lambda on the left or on the right, you expand. And the hope is that this can be shown interderivable with the eta conversion rule of Abel in his paper. For S-prop, Coq does it by using a syntactic check. So when a conversion test fails, it tries to find out the relevance of one of the two terms, and if one is irrelevant, it just succeeds. So there are enough syntactic information left in the terms with the relevance annotations to decide this in a sound and complete way. So it could be also added to the untyped conversion. It's just not entirely clear if we can develop the meta theory without without seeing this on type conversion as an optimized version of the type conversion.
Okay, I see. So I was going to ask essentially, what about trying to just formalize the meta theory of whatever it is you did implement? And so I guess, all right, you think maybe the easiest way is to show that it's the same as the typed conversion. Okay.
Yeah, I think it's tricky. I mean, I think we tried this already when I wrote my PhD, and I think Hilfdin Gogen wrote something related. I don't know how much this helps.
So there is TPOSR, so this type parallel one-step reduction, where you define a third system which mixes typing and reduction, and you do kind of at the same time a confluence and subject reduction proof. So then you have confluence of type reduction and subject reduction at the same time, and you can show that erasing this gives you a type conversion, and that you have enough typing information to produce typed equality derivations. But it's really based on reduction, so I'm not sure you can extend it with eta rules that easily.
But that's what he did. It was the main application. I mean, so it was the main application of this typed operational semantics to justify.
Eta? So I need to look at it again. I didn't think eta was handled by this methodology.
Okay, it's a while ago, but that was certainly I thought the main challenge. I mean, that was a challenge at the time because we were in the past, in the last millennium, we used untyped reduction, and at this point in the history, we then want to prove the equivalence, right? I mean, now I would just say that's a historic bug and just get rid of it. And it's maybe interesting from an archaeological point of view.
A little bit, yeah.
But nothing else. So I mean, get rid of untyped reduction. That's basically. But so I had another thought. I mean, this is very nice, and I mean, I'm quite impressed what you have achieved in sort of like basically re-implementing Coq, but doing it in Coq. I mean, in a verified way. And I think that's a very important and reasonable endeavor. But I'm thinking a bit further. I mean, if we can start from scratch, okay, that's maybe not the Coq way, but okay, if we could do this, then isn't there a way to have a really much smaller trusted core? Yeah, for example, I mean, we have all these ways that we reduce all sorts of very clever type theoretic constructions to W types. And should we not be able to exploit this by having a very small core? And for example, I mean, we showed like so inductive families and even inductive families and so on. They can be all justified just using W types. So there isn't, I mean, shouldn't it be possible to have a really very small core and then justify all sorts of really interesting and very powerful type theoretic principles to it?
Well, there's always a tension. I think the liberty you get by formalizing this is that you can have a large core, but know that in principle you could always go back to the simple one and study the meta theory just of the simple one. The rest is kind of elaboration engineering.
Yeah.
I think that's the ideal situation, but I don't believe that you can. I mean, it might be possible, but it would be hard to have a course that just talks about W types and still an elaboration that can hide the fact that you're elaborating all your inductives and indices and so on and pattern matching down to that. But
I mean, what you need is some sort of extensional import from extensional type theory. There are certain things you can prove propositional, but as we've seen, there was a talk recently, right, that we can then show that this maybe doesn't matter. So that's something we need. Right?
Yeah. But you will anyway need the proof that that the higher level complicated type can be reduced to a simpler, type theory can be reduced to a simpler one.
Yeah.
So you can always choose if you want to implement the very basic one or the more higher level, but with a good justification.
Yeah, because I mean, in a way, the presentation of type theories have the schematic inductive rules in a way are not really small in some sense. They're still quite complicated. And I mean, I don't maybe not so much in Coq, but certainly in Acta, there's lots of pressure to put in some new features. And each time when you do this, you endanger soundness again. Right?
Yeah. So better formalize it.
Yeah.
I think that, I mean, it's certainly the case, isn't it, that that's the way that Lean is doing things, right? I mean, its core, which is implemented in C++, is basically, you know, a fairly basic Martin-Löf type theory with inductive types.
Yes.
Yeah,
But still
I also would like to reduce it just to W types, which I agree would be great, but they don't quite do that. But they have a very small core, and then everything else is Lean.
Right,
Yeah,
but I agree with
eliminators.
Sorry, Jesper, go ahead.
Yeah, the related question, because, well, you're saying, talking about Agda, so suppose someone would be, I mean, I have a friend who would be working on doing a similar project for Agda. What is the main lesson that you have learned from this? Or what is there anything you would have done differently now that you have done all this work? Like maybe with regards to the syntax representation or the representation of the typing rules, or is it, or was it all like straightforward? Yeah, I mean, implementation of the system that you already knew.
Most things were straightforward, but I mean, it's just long to formalize confluence, for example, things like that. So about the syntax, we kind of started with a constraint that we wanted to handle exactly the syntax of Coq and not start with a translation to a generic framework. I think it would have helped if we could have used automated substitution, weakening lemmas, and so on. But actually, we found out that changes to the internal representation of the syntax would, I mean, it would be impossible to automatically generate these proofs. There are strong invariants about the syntax. So yeah, it might be better to look at translations to, I mean, elaborations into simpler type theories at the beginning. So we could do this meta theory proofs on a simpler theory. Yes.
Right. Yeah, if I can ask another question. So because you're now talking about, well, doing the meta theory for this and and using this for producing a verified type checker. Are there also other applications of this? And I'm thinking specifically of like writing verified tactics or plugins for Coq that operate on this, or that you can prove correct by using these typing rules.
Yeah.
And
so
is it usable for that, or is that still hard?
It's usable. So I've shown you an example where I can give a term to give just a term and a type and let the type checker figure out the derivation. I don't think it's very practical. I mean, it's a very bare bones interface to the calculus where you have the Brownian indices. It's all very, very concrete. So tactic languages like LP or LTAC are better suited, I think, for usual tactic writing. However, it gives you the ability to verify translations like parametricity translations. I mean, fully in the system and give access to the users thanks to the verification machinery. And for that, I think that's useful.
Okay.
And the type inference is actually used in one of the translations because the syntax is not ideal, and at some point you need to infer type annotations to produce the resulting term. And that might happen in those other translations. Yeah.
Okay, right. But if you want to write actual tactics, you would rather use a more higher level representation.
Yeah. I mean, you could imagine building a language, a high level language, and verifying it with respect to the typing semantics.
Right. Yeah, that would be interesting, I think.
That would be fun.
Okay, thanks.
So have you tried running your extracting a new kernel and running it to check proofs, like real proofs, not just 2-line things you wrote?
Yeah. So the type checker can check the hot prelude. So not 2 lines, but up to is equivalent identify. So prove that you can promote adjoint equivalences to equivalences, which is a fairly big file already with universe polymorphism, pattern matching. Yeah, and it was just 10 times slower than Coq, I think, which is
Okay.
yeah.
Yeah, no,
for
that's not
something
so
that was
bad,
not
yeah.
optimized, it was not so bad. Yeah. But yeah, as we are missing eta conversion, so either you hack the thing so that you still allow the input thing to have, I mean, you cannot do type checking because we don't handle it. But if you want to do erasure, for example, of things that have that use eta conversion, you need to hack something. So we are not testing on very big developments because most things use eta conversion or template polymorphism in one way or another. You need to make your development specific. I mean, change your development specifically to check them or erase them.
And do you use these features in your type checker? I mean, could you type check the type checker with itself?
Yes. I mean, it's easy to avoid eta conversion in a single development, and we don't use template polymorphism. So yeah.
So did you try type checking it by itself?
No, we did not try it. Well, it was broken for the last few months. So. But yeah, for sure we will try that. Yeah. I think we tried. Yeah, probably we tried last year, and it ran for 20 minutes, I think. But it just gives you a yes or no answer. It's not very exciting.
Well, at least it terminates. Right?
Yes, it does.
Something, and so you gave it enough fuel to not get blocked on the assumption.
So I did not run it inside the Coq. I ran the extracted version, which has no
the
fuel.
extracted version, right? That erases all the accessibility, I guess.
Yeah. So it's not.
Yeah, right. Okay.
It's not the most certifying way to.
Right. Yeah.
Yeah.
So running
But
it inside Coq would be a lot slower, I guess.
Yeah. It would be huge. Yeah, especially since inside Coq you don't have an optimized representation for reified terms. Or in particular reified strings that appear in names. The blow up in size of doing things only inside Coq and not in the extracted version is too much, I think. Okay.
Okay, well, maybe we should thank the speaker again.
Thank you.
And I'll stop the recording.